Good evening to one and all who are attending for this talk on uh, interaction with industry and what the challenges faced by Indian defense industry in the field of manufacturing. So I would like to introduce today's speaker, Mr. Ayush Verma. So he has completed his MTech from Material Science and Engineering, Material Science and Technology from Defense Institute of Advanced Technology, Pune in the year 2017. Later, he joined L&T, where he is into welding department in the L&T's defense business as a postgraduate engineer trainee in Mumbai. He has completed 8 successful years, and right now he is the head of the Department of Welding Metallurgy in L&T Defense Pune. He has piloted many development projects for L&T in the process development, welding, and metallurgy. He played an instrument role in the development of welding process and automation for many developments in production in the defense projects, including armor steel, aluminum, and metal matrix composite. And he has around 6 journals, publications in the field of friction stir welding, laser welding, and high entropy alloys. And right now, he's pursuing his PhD as a sponsor candidate from DITE, if I'm correct. Okay.
Yeah.
Okay. And Mr. Verma, and stage is all yours. You can start your presentation.
Thank you, Shiveen. Hello, everyone. Good afternoon. I hope I'm audible to everyone. So a brief introduction have already been given by Shiveen to all of you. So let me tell you briefly how I started my journey and how I landed up in L&T. So I completed my MTech in 2014 from Material Science and Engineering Department. And therein, through campus placement, I got selected in L&T. And I was one of the few fortunate students all over India who got selected there. And since then, I am with L&T. Seeing my academic career, I did my master's in production engineering. Then I changed my field to medical science and technology. And seeing my keen interest, they had offered me a PhD, as a sponsored PhD program. So in 2017, I joined a sponsored PhD program. And right now, I'm about to finish it. Like I already submitted my thesis and all. So I'm about to finish my PhD. So since 2014, it's a wonderful journey with L&T. A lot of freedom have been imparted. A lot of like I have been given an entire department to handle. So a lot of freedom they give, and like the kind of pressure which most of us are aware of. Like in industry, you have a lot of pressure. So those kind of things, at least what I feel, is not there, because to be frank, I love my profession. Like metallurgy is my passion, sort of. So with that, I would like to share what all learnings in past few years, or what all challenges at L&T, or what Indian defense is dealing with. Like I am from industry as well as I am into research. So I know what my pain area is when I have to implement something which I read. So I'll move on to the content. So a brief introduction I'll give. What all is there in Indian defense sector? Uh, what are the challenges related to materials? What are the challenges related to manufacturing? Brief challenges about land system, naval system, and aerospace system. So these are the main focus areas. So what like Indian defense sector is basically divided in these 5 parts. Weapon engineering system, flight systems, which includes missiles and aerospace, land systems, marine equipments, and electronic and military communications. So I'll only be touching about like weapon system, flight system, land system, and marine system. Communication system and all I'll not be touching on, but it also is one of the pillar on which Indian defense and aerospace sector is standing. So in weapon systems, like small arms, these kind of things are there. Missiles and like jet engines you are aware of. In land systems, uh, tanks are included, launchers are included. In marine equipments, warships are there, submarines are there. So these kind of things are there in the portfolio. So when we talk about defense, what is the end requirement of my customer? My end customer are either from Navy, Army, or Air Force. Or sometimes the requirement comes that the same system has to be given to the Indian Army also, as well as Indian Navy also. So like a wide range of applications are there. Like this system you can see, this is a modular bridge kind of thing. Like this is a bridge. If there is a small lake is there, or a small uh, like a road is not available for commuting. So how will your strategic weapons will move on into the other territory, like from place A to place B? It won't be possible. So uh, so such kind of products are there. Like it needs to be deployed on land as well as maybe in the area which is like water is there. So you can understand the kind of pain while designing it went into. Like marine application also we need to think of that the system should work. Then the diversifications. In India, a wide variety of temperature ranges are there. You can have 60, 70 degrees centigrade temperature in Thar Desert, as well as minus 60, minus 40 degrees centigrade temperature in Leh Ladakh. So in all those diversified environment, the system should work in. So sometimes it becomes difficult to make such a versatile system which can withstand both these requirements. And accordingly, designing the electronics part, it become bit tricky. Moving on, whatever systems we design, so that needs to have serviceability and maintenance, and like they should able like the end user should able to maintain it and service it, because what will happen at the time of war if some breakage is there? So right now we can always go there and repair the thing, but what if during war something had broken and it need to be repaired? At that point of time we might not be allowed to go there and repair. So we need to train the personnel, and that how it can be repaired, and repairing should be quite easy so that they can easily able to repair it. So that is again a challenge. Design a system with the which the end user can repair. Reliability becomes an issue because the same system has to be fired at minus 40, and the same system should fire at 60 degrees centigrade also. So that is also a challenge, but that's what the customer demands. Off-road capability is one of the key factors which all the systems are designed for. You can take TCT-5 on which Agni missiles are launched. So it's a mobile launcher which you can, like it's a kind of truck on which the launcher is mounted, and it can fire from any place. So systems has to be accurate and should have off-road capability. And then comes the seawater and marine. So corrosion resistance, anti-fouling, these kind of things are become of prime importance. So these are the things which the end user wants us, that their system should take care of all such 6 issues. And that is the prime importance. So, talking about what all technologies which we work with these days. So I could able to divide into three parts. One is nascent, being built, like which has not matured and still there is scope of improvement. And third is already matured, like there are some development going on, but fairly we have reached to that level wherein our end user are happy with the kind of systems which we are delivering as of now. So one thing which is still nascent is advanced materials and optronics. Uh, Ballistics radar systems are available, but there is a lot of scope of improvement. Advanced processing, hydrodynamics, use of AI is still not being is still not there in the Indian defense industry to a greater extent. Might be a small pilot project would be there, but not to a great extent. Then fairly mature as composite control systems, ruggedization structures, servo motors, navigation systems, networks. Navigation system, because of ISRO, a lot of good things had come up for Indian defense. Um, so any development which happens follows this cycle. So what is the mission statement, or I would say the end requirement of my end customer? So on that basis, problem statement or mission statement is defined. Over that mission statement, we develop a concept model or concept development happens. From concept development, the system level design happens. From there, a detailed engineering drawing is developed. And then a prototype is developed. It does not happen that you make a model and you directly start producing. Like you cannot directly bulk produce. That is what is happening for most of the automobile sector or in any sector you say. But typically in defense sector, you need to make a prototype, you need to prove it, and proving may take 7, 8, 10 years. From my experience, I can tell you, I had seen few of the systems which are now in serial production, but the initial development happened in year 2000 or even before. Some of the systems were developed in 1980s or 1990s that are now in serial production. So such a long cycle is there. One system I'm particularly aware of, for that we are doing testing for last 5 to 6 years. Such rigorous testings are happening. So why such rigorous testings are required? Because of the reliability. It has to fire when it is required. Else, the system should be idle, should not be in use. But when you click a button, it should do the required purpose. When you buy a car or a laptop or any, for that sake, any item, what is the warranty? What the company offers? Maybe 1 year, 2 years, maximum 5 or 7 years, or at max 10 years. But at L&T, we offer the warranty or we take care of the equipment for next 25 years. The systems has to withstand and should do the intended purpose for next 20 to 25 years. That is the commitment what we gave. And for that sake, any of the defense sector give. Only then the system is acceptable. So that's why, because such warranties are required or are expected from the end user, so the cycle becomes very long. So then once the prototype is proved by all the testing, then the serial production happens. And in serial production also, it is not like that you have to make 1 lakh components or 10 lakh components. Serial production here means maybe 30 odd jobs, 50 tanks, 30 missile systems. So something of that order, not something which will go in lakhs and crores, nothing like that. Then the product support is also required, and the system upgradation. Time to time, system need to be upgraded. So that's what the cycle is for typically any defense equipment. So for that, what all materials are required is uh, we deal with metals, ceramics, polymers, and composites. Mostly we deal with metals. I would say 90% of the bandwidth or the consumption is of metals. Composites next 5 to 7%. Then rest is ceramics and polymer. That's how the typical bifurcation is as of now in defense. Composites and polymers are mainly used in aerospace, and rest all like for naval application and other things, metals and ceramics are used. Ceramics especially are used wherein high temperature applications are required. So when you design, or when the end user give you some his expectation, so based on that expectation you need to select a material, like out of like then once you have selected that, you have to go with metals. So in metals, uh, people take care of mechanical and physical properties only, but uh, a special need or a special care need to be given for chemical properties as well as manufacturability. Sometimes we have seen cases wherein bimetallic corrosion happened in the system and the systems failed. So those kind of things need to be looked into. So strength, ductility, toughness, hardness, strength to weight ratio, these are of prime importance. Physical properties also play an important role, but most importantly, these chemical and manufacturability are required. Sometimes, like I have selected a material, my requirement is ballistic properties or are typically very high strength. But as soon as I increase the strength, my machinability goes out, formability goes out, weldability, we don't have welding consumables, which can give you such a high strength. So far, I am only aware of maximum strength which can be achieved by welding is of the order 1100 MP or so, not more than that. But most of the systems which are being used does require a strength of 1700 MPa, 1600 MPa, or more than that. So these things we need to keep it in mind when we are selecting a material, which most of us don't. And after like maybe the systems work fine for 2-3 years, but after that the degradation starts. These are some combinations or the materials which typically any defense sector deal with. In special steels, we work with high strength low alloy steel 690 QL, 960 QL material. So they have a strength of 690 YS and 960 YS. Then for marine application, DMR 249A, AB2 material, NVF 690. And these are some other special steel which are required, 15 CDV6. Armor grade steels are extensively used for tanks and for many other applications. Most of the vehicles which army use should be made up of armor steel or composite products for ballistic application. For corrosion resistance for naval applications, we either go with aluminum or stainless steel because we don't have any other option. So SS or 15-5 pH or 17-4 pH, or sometimes duplex steel, depending upon what kind of application we are going for. These grades of aluminum we have worked with so far. One particular grade of material which is extremely close to my heart is 7004. See, before that, like 6000 series, 5000, 4000 series, they don't give the required strength which we aim to reduce the total weight of the system, strength to weight ratio. 7000 series gives the highest strength, but the problem with 7000 series is it's not weldable. It's not easy to weld. So a lot of problems people face while joining of these materials. And at LNT, we had like welded lot of materials from 7000 series. Not only conventional welding like TIG, MIG as well, but we have gone into friction welding as well as laser welding. Some other like special material which these days or most of like we are using is our titanium and super alloys for high temperature applications like jet engines and all those, like wherein the systems are going at a very high temperature. So and they at that temperature we need the similar strength. So then we are going on nickel based systems. Then aluminum bronze, silicon bronze. So these materials are also being used. So what are the problems when suppose we have selected one particular grade of material? Then again the problem comes MOQ, minimum order quantity that is required. If I go to a company and I want to buy 5 kg of material, literally they will kick me out of the company. Sir, we don't sell you 5 kg, you need to buy at least 5 ton or 50 ton. So sometimes that's the case. So while designing a system, first thing is you need to see whether the functional requirement is getting fulfilled, and as well as with that, that material is available in India or any for that sake anywhere in the world in whatever quantity you are manufacturing it. Since it being a defense sector, the order quantity is very small. Maybe for 10 systems it is required, so it could be 5 tons only. So sometimes it becomes very difficult because the quality requirements are very stringent. You cannot accept a substandard material. A lot of cases has happened that the systems had failed because they had used a substandard product. Radiography requirement and NDT requirement are so stringent that even a small porosity sometimes is not acceptable. Other challenges is like one of the problem which most of the systems faces is wear. When we like a missile system is there, we had fired a missile. So some erosion and wear takes place in the chamber. What then? We need to fire again second missile from the same chamber. You cannot throw away that chamber. So all those aspects need to be kept in mind. Compatibility, like electrochemical compatibility is an issue. Sometimes while designing a system, we tend to forget that these two elements are not compatible. And we keep those systems together. After a period of time, 3-4 years, we get to know from the end customer some corrosion had happened. And then the system is gone. Another issue is reliability of the material throughout the service life. Even if it undergo a lot of thermal cycles, mechanical cycles, it need to perform its intended objective or intended function, even after 10 years, 15 years, 20 years. So accordingly, such materials need to be selected that even if the temperature goes up at 300 degrees centigrade or 500 or maybe 700, 8000 degree, even then it should do its intended purpose. So that poses a problem. So cost of material is a bit high, and thanks to the war scenario which is there in Ukraine and Russia, most of the raw material costs had gone up. I can share an example of titanium. Titanium, which we used to buy at 5,000 rupees a kg, is now 10,000 or 12,000 rupees a kg, or even more than that. Another serious problem which is there in the defense sector is most of our equipments are from Russia. Russia being our close partner, so a lot of defense equipments they had given us, or we had bought it from Russia or USA, and now they are 15-year-old, 20 years old, or maybe more than that, 30 years old. And what the Ministry of Defense is asking is, can you refurbish those particular areas which had worn out or torn out. So there comes the reverse engineering of materials. Therein, we have to do the reverse engineering, replace it with the adequate material. So that is a very gray area. Sometimes it becomes very difficult to identify what they have used and what we should use. And a lot of development is required in that particular region. When we use with such vast variety of materials, so different combination of materials, like we end up welding it together or joining them together. I can still remember at one particular joint, I had to weld aluminium with steel. It was a horrible experience for me, because the joint configuration is such that I cannot use solid state welding. I have to use conventional welding process. So such challenges are there. So typically joint design material thickness, we need to check in when we are working with dissimilar materials. Majorly different melting point and thermal expansions and contractions. Because of that, a lot of crack generations and some other issues are happening. Stresses on joints due to fixturing and constraints are there. Then different intermetallics are formed. So basically, when we are joining two materials, it becomes very hard. So a lot of development or a lot of R&D we do, that how to join two different grade of materials. Whether a special filler need to be made specifically for joining, that we have also done that. We had made a special consumable wherein which can be used for joining these two different grades. So these are the lists which we feel that are the main area of interest. Like from here, what all points are missing in industry, wherein we are seriously struggling to develop, or we want some development to happen. These points I have listed down from this particular region, wherein uh, most of the Indian defense sector are or require your support or your collaboration. So most of the systems, eh, from design level, when we design a system, we keep it in mind that it will be made first time right, that no repair will happen. But that is not the fact. When we manufacturing it, there are number of times or number of iterations had to be done, and many times we end up repairing the same joint twice or thrice. But sometimes the end customer demands that only one repair is allowed or two repair is allowed. Beyond that, the material is not usable for us. You have to throw away the material. So a lot of R&D, like we have also done some work that how many times a particular material can undergo repair, once, twice, thrice, and how the material degrades over a period of time, and how it degrades when we do multiple repairs. So that is a gray area wherein a lot of research can be done. Most of the fatigue estimation which is available even at industry or in the published work, uh, they don't generally take welding, like consider welding. They consider that the joint efficiency which any weld gives is of 100%. Sometimes that is not true. And most of the fatigue life is calculated, like they don't keep in mind the welding. So specifically welded component fatigue life is of prime importance, because all these systems which I have shown on the left side, they go number of cyclic loads. On these are the bridges on which tanks pass, and the weight of the tank is 70 tons. So you can estimate the kind of loading or the fatigue these bridges undergo when a 70-ton vehicle is passed on it, that too with a certain speed. Most of the systems which are available are mobile, and weight reduction is required with cost effectiveness. A lot of time these bridges are previously these bridges are made from steel, but because of the weight constraint they need to change the build material to aluminum. In aluminum also now they further want to reduce the weight, so the requirement is such that you further reduce the weight, maybe from 5 ton to 3 ton, so that the mobility of the systems is easy, deployment of these systems are easy. So that is one requirement which is always in demand by the end user. They want a lighter system, they want a stronger system. Uh, Next point is very limited research is available, or very limited materials are available which can be used in directly in industry for high temperature applications. That's what it is like. Specifically high temperature application materials are still not available. Most of the exotic materials like titanium and all, we are buying it from either Russia or USA. We don't have the capability to manufacture them, and even if we do, the cost which they the material which is being produced in India, the cost is extremely high. Sometimes it become more cost effective for us to buy it from Russia directly. So still we don't have those kind of capabilities. So this is a gray area which people can focus on. Ballistic properties, like at every slide you will see the ballistic properties. Very limited research have been done on ballistic materials, specifically lightweight ballistic materials. Lot of development can be done on lightweight ballistic materials. Even at L&T, we have collaborated with many mills wherein we need such materials which shows good ballistic properties. And the requirement is from the Ministry of Defense is that lighter the weight, the better it is. Not only for soldiers, but for vehicles also. Higher strength material is required to reduce the weight of the entire system. So that is again problem. Like higher the strength, lower the ductility. So you can produce as a material which can show 1100 MPa, 1500 MPa strength, but your ductility goes down. So you'll not be able to form it, bend it, or make the entire component out of it. It becomes very difficult. Maybe at a smaller scale, it is okay, but when you have to build a system of 10 meters, 15 meters, 30 meters, some of these bridges are 46 meters long. So then a lot of ingenuity and ductility is required. Moving on, the challenges for manufacturing processes are like, so far, most of the defense sector is reliant on only three processes: arc welding, that is SMAW, MIG welding, and TIG welding. So far, they are not comfortable with laser welding, friction stir welding, or laser cladding for that sake. These are beautiful processes, like they good, excellent properties. In fact, most of the automobile, like in automobile sector, most of the joints are done by laser welding. But so far, Indian defense sector has not accepted these particular processes, because a lot of testing need to be done. Forging is one area wherein a lot of research is required. Whatever exotic materials I have mentioned in my previous slides, forging of those components are not easily available, at least in India. Another gray area for us, wherein I have particularly seen systems failing, residual stresses. When we do a lot of machining, bending and welding of aluminum structures, so at that point of time, over a period of time, residual stresses or SSC kind of thing, like stress corrosion. Uh, that happens, and we had found cracks on the systems. So still, we lack a lot of knowledge in that particular area. Sometimes what we now are coming up is we want to avoid heat treatment. We want to go with vibratory stress relieving because it has shown limited success or some success in that particular, like avoiding of heat treatment. See, one cannot do the heat treatment of, like, you all of you might have seen the heat treatment furnaces, the size, the chamber. What is the maximum size which can be built? Just imagine uh, doing a heat treatment of 46-meter long system. Will it be possible or feasible or economical? But it has to be done. So we are looking for alternate of heat treatment, which will give the, like, the required properties, specifically stress relief. Shrinkage study is missing, like uh, because of unplanned shrinkages. Like we had cut the system without green, and when we have welded it, we found the entire assembly short by 10 mm. Then you have to scrap the entire assembly. So a lot of shrinkages are happening during welding of SS, aluminium, plain carbon steel, which we have neglected during manufacturing, and that is the learning what we got. So some data generation we do at our end, that if this is the component and this much amount of welding is going on, so where and what amount of shrinkages might happen. So maybe a special software can be developed, or some research can be done on it. Use of AI is very limited for quality measurement system. Uh, One particular area of interest wherein I am working on as of now is image-based processing. Using a mobile camera, we can detect a weld defect. So those kind of developments are not happening. Like for a long time, we have been struggling to find equipment which can do the image processing for us. We just have to scan the region, and it should tell us the kind of defects, what is there, a porosity is there, crack is there, what are the sizes. So those kind of systems are not available. Most of the industries have moved on to automation, robotic automations, or some kind of mechanization. But defense sector being a project-based industry, so one component might not be similar to the other component. So they are in using a robot wherein you have to do a lot of programming and the changes has to be done. Sometimes it becomes not economical, and if we do that job using a robot, it will take maybe 5 hours. But when we manually ask a welder to weld it, he might be able to do it in 3 hours, because the kind of programming required, at least for one system, you have to program. So uh, frequently cobots are there. So collaborative robot, wherein the programming time has gone down, but still the cost is at least 5 times higher. If I can buy a robot for 5 lakh, the cobot of that robot of maybe 1 meter size, the cobot of the same size will cost 5 to 6 times more. So sometimes it becomes very difficult to invest in such kind of processes, wherein low cost automation would be a boom or a boon for us or for the Indian industry. Moving on to the land-based system. In land-based system, tanks are there, rocket launchers are there. You can see these launching or the firing taking place. So mostly which are fired or which moves on the earth are called the land systems. So in land systems, again, it need to pass the desert condition environment, high altitude, Leh Ladakh, thanks to our neighbors, and the coastal regions. So, developing a system which can take care of all these three things or three environment is very difficult, and it takes, like, the cost is extremely huge. You can see the firing happening at that time. So all these material gun barrels and most of the systems, wherever, like here you can see firing happening, most of the systems, like we fire something or the other. So high temperature resistance are required not only in these regions, but the regions which are built nearby. The main requirement by the end user is the system should be compact. So ultimately you end up selecting a material which should show high temperature resistance. And very limited research is available. High performance smart materials are used in these missile systems, actuators like ferromagnetic shape memory alloys. So a lot of scope is there in terms of ferromagnetic shape memory alloy. So far, deep hole drilling machines, like a lot of work can be done, development can be done. Still, we are struggling to have precise deep hole drilling machines. Ballistic properties, I told you that all the systems which we design should have ballistic properties. High precision machinings. So therein also a lot of R&D, a scope of work is required wherein high precision machining can be done. Distortion control is a must. Suppose if this missile is not guided, and there are systems wherein the firing is not guided. Like guided means the whatever inclination you have set, so it will follow that particular inclination. So even if you are out, suppose the barrel is out by few degrees, and if it is a short range missile, so if they repeat, or the ability to hit the target within 1 meter or 5 meter is lost. A small deflection by a few degree will lead the rejection of that particular component because of the distortions, well distortions or machining distortions. So very precise manufacturing is required, which is not happening. Life cycle improvement of gun barrel. That is an area wherein most of the people are working, or they want to improve the life. There is a limited life. Maybe after 500 firing or 1000 firing, you need to replace the barrel material. If any research can be done, maybe any cladding for a length of 4 meters, 6 meters, 5 meter can be done inside the barrel, which will improve the life. So uh, ministry will immediately accept such kind of things. They are willing to immediately adapt. And some work even we are doing to improve the life by changing the material as well as doing some cladding inside it. Uh, Bio warfare resistance, like a lot of development is happening, and like all these tanks, they have filters, or they are designed in such a way that bio weapon will not work even if someone fires a bio weapon on them. So people sitting inside the chamber should be safe. So that is the intended purpose, and a lot of work is going on, and still there is scope of lot of work. Moving on to the naval systems. Naval systems specifically work on sub-zero temperature. So designing or selecting a material, lightweight material for sub-zero becomes a challenge. That too, it should have a good corrosion resistance. Fatigue life estimation at sub-zero level, very limited work is there. Weight reduction. Another important area which the submarines or unmanned drones, which we are working on, or which we want some development to happen, is the stealth material. So still we don't have such kind of capability. Uh, and lot of scope of improvement is there. Then fuel cell development, a lot of development is done by NMRL lab, Naval Material Research Laboratory, Ambernath, Mumbai. But still, a lot of scope is there. A lot of efficiency improvement can be done. When we talk about naval material, anti-fouling is the area which most of the shipping industry is the pain area, like, and um, that's a main pain area. A lot of rework, or a lot of not rework, I would say, a lot of maintenance they have to do just to avoid the anti-fouling, or to have the anti-fouling property. Every year, lot thousands and thousands of, or crores of rupees, uh, shipping industry put in. Uh, Coating for wear, thermal and corrosion. So that is of prime importance, and lot of work need to be done for coating processes. Uh, Material for nuclear applications, like people are exploring. Even at L&T, we are exploring. We are part of few projects wherein nuclear capable submarines are being developed. So whatever small contribution are required at whatever level, uh, all over India, whatever scientists can do, they are doing it. So one major problem which come up is the what material need to be used, because when we talk about submarine, they have a very limited space. It is a very confined space area. And making a nuclear reactor is a different thing, and making a small submarine which have those kind of capabilities, it's very difficult. So new materials are required with enhanced properties these days. Moving on, aerospace is the last area which I have intentionally selected, because some work I have done during my PhD on it, and still a lot of uh, improvement is required. Weight reduction is one, composites, lot of metal matrix composites we are working on. So still a lot of improvement can be done. Uh, Ceramic thermal barrier coatings are being used, and and still, because we don't have those kind of capabilities, so having material for high temperature, so these thermal barrier coatings and ceramics at a lot of places are required. And to be frank, only few key players are there in the industry which can support for these kind of thermal barrier coatings. I can name them on my fingers. Such a scope of improvement are required from industry as well as from academy. Structural health monitoring systems are at all not available in India, and a lot of scope of improvement is there. Self-healing material is one thing which most of us are talking these days, and we seriously want to use such kind of materials for our application. Uh, for propulsion systems, we had started using high entropy alloys. Like, we have proposed the use of high entropy alloys. Most of us, or most of you, might be aware that so far we could not able to make a jet engine ourselves, and we are reliant for most of the materials from outside, from other countries. We buy the material because at such high temperature, only few key people have the know-how to develop the kind of materials which are required. So still we are buying it from outside. So that is one gray area wherein a lot of scope of improvement is required, and a lot of you can pitch in and help us. Piezoelectric thrusters and actuators. One particular area which Indian defense sector is lacking is use of 3D printing for aerospace application. Airbus, Lockheed Martin, they have all using 3D printing parts. But so far, we are at like Indian defense sector is not willing to use 3D printing because they don't trust like it will be able to pass the required testing. So that kind of trust is not there. And maybe extensive testing can improve those things. So this is one gray area wherein a lot of people at industry are working. Wipro has its own 3D printing plant. L&T has its own. Even Tata's have their own 3D printing. Uh, Bharat Forge has their own 3D printing plant. But so far, we have not successfully implemented it on job. Whereas other industries or other countries are using it. So summing up, a lot of challenges and difficulties are there. Like these difficulties, whatever research area I have specifically mentioned, are the challenges which in defense sector, Indian defense sector is dealing with, wherein with a lot of research and a lot of you and enthusiastic students can help us come out of it and make us self-reliant. What is the motto as of now for present Indian government? Atmanirbhar Bharat and Make in India. So with that, I would like to thank you, and I have mentioned my email ID. Maybe you can get in touch with me, and I am open for any questions, whatever you have.